Um, so hopefully all of you remember this question. It is a little bit longer, so it's maybe difficult to, I mean, it will be time-consuming to read this whole thing, but basically what we have is a one-channel, two-rank system, right? One-channel, two-ranks DRAM system, and each channel has its own memory controller. We have 8 banks, and you were asking about the timing diagram. Which part is that exactly? So let's see what it says here in the question. DRAM is refreshed every 64 milliseconds, running by command from the memory, which occupies command bus on the associated memory channel and the associated bank. Okay, so a single refresh command will only refresh a single bank from that rank, right? So that means you can, every 5 nanoseconds, the memory controller is free to issue different refresh command to different bank, or the same bank if it's ready, if it's completed the previous refresh operation, right? So to answer your question, every 5 nanoseconds, the memory, you can expect the memory controller to put a refresh operation to any available bank in any of the ranks available on the system. So so let's say this is time 0, and time goes this way. So if, for example, here until 5, you have a refresh to, let's consider only a single rank, one rank, right? So you refresh, let's say, bank 0, rank 0, bank 0. After 5 nanoseconds, you can also put here another refresh command to refresh bank 1 or any other bank. So you can pipeline those, right? But here, at this point, you cannot refresh bank 0 again because bank 0 is already being utilized. It is already being refreshed. So we should wait 40 nanoseconds. Right. To issue a refresh to the same bank, you need to wait at least 40 nanoseconds. So this is a little tricky, actually. I think it is. So it is tricky, but I believe it is clearly defined here because in C here it says what data bus utilization across all memory channels is directly caused by DRAM refreshes, right? So what you say is kind of an indirect result because DRAM is being refreshed and basically you cannot access this bank, so you cannot read anything out of it. You cannot utilize the data bus. That's true, but it is not directly because of refresh, because the refresh command itself is not using the data bus. Yeah. You only give the address, the bank address, to the DRAM. The memory controller only gives the bank address, and the data bus idle otherwise. So if you have another rank, for example, this data bus can be utilized by the other rank if it's not under refresh. So you can't say that the refresh operation is utilizing the data bus, actually. It may cause the data bus to be underutilized, but it is kind of a side effect. It's not a direct effect. Yeah.
When we issue a refresh command to a certain bank,
so it depends on what kind of refresh command you're issuing. So in DDR3, DDR4, in real implementations, there are bank level and rank level refresh commands. So if you share rank level refresh command, all the banks in a rank are being refreshed. So yeah, so the entire rank is unavailable. But if you issue per bank refresh, which is available with DDR4, I guess it's not available in DDR3, then you can access other banks. Yeah. So here in the question, it clearly says that associated memory channel for 5 milliseconds and the associated bank, right? So this means this is a bank level refresh command.
So this is based on a paper published in 2018 DAC. It's variable refresh latency. So the main observation in this paper was, as we described in the question, is you don't have to wait for the full refresh latency. So what is refresh latency? So, okay. So this is your time axis. I'm just drawing this for one single row. So this is your refresh interval, right? This is just some extra knowledge about this question. And this is your refresh interval. And when you start the refresh operation, it also takes some time. This is refresh latency. And this paper tries to mitigate this refresh latency. And the main observation was that you can actually get a pretty good restoration in the voltage level if you just wait for the 60% of this latency instead of waiting the whole thing. So the remaining questions are going to be based on this observation. So in the first one, the question tells us that here we see a graph. On the y-axis, it's maximum number of partial refreshes. So when we just use 60% of refresh latency, it means a partial refresh. And we cannot keep doing this for the whole refreshes. So this plot means, as described on top of that, if I see a value 1 here, then it means that after a full refresh, I can do only one partial refresh, and the second one should be full refresh again. And if it's 3, I do a full refresh, and I can do 3 consecutive partial refresh for the other 3 refresh intervals, and then I need to go back to full refresh again. So this is how this works. And here, what we need to calculate is how much time does it take for a bank to refresh all rows within a refresh interval, right? So here, we only have one single refresh interval, which is 64 milliseconds. And our refresh latency is, the full refresh latency is described as T, and the partial refresh is 0.60, the 60% of that, right? Okay, so what we do here is actually just multiply and add them up. So here, as you can see, like 10%, 60%, 30%, this is the whole distribution of these rows. I can, for the 10% of the rows, I need to fully refresh those every other interval. So it's like interleaves between partial and full refresh. And for 60% of them, I need to fully refresh them after every 3 partial refreshes, right? So what I do here is, this 0.1 comes from 10%, and then half of them should be partial, half of them should be full, right? And for this one, 60%, 0.6, and then 75% of the refreshes should be partial, and 25% should be full refreshes. So I just calculate these, and then add them up, and then it gives me the refresh latency of a bank as this value. So I hope it's pretty clear now. And a lot of people already found this exact number in the exam, so I just assume that it's easy. But if you have questions, you can ask anytime, interrupt me. Okay. So based on this observation, we need to understand like what is our benefit here in this paper. So for that, we need to come up with a good baseline, right? So in our baseline, we see that 90% of the rows can be refreshed at every 128 milliseconds. And 10% of the rows can be refreshed at 64 milliseconds, right? So here what we do is we want to compute the refresh overhead of the baseline where we don't have any partial refreshes. So here I have the value for a single refresh command, which is this, where n is the number of rows in a bank. So refreshing the whole bank is going to take 0.2 milliseconds, right? Okay, so again, I do the same thing that I do in this second part of the first question in the basics. Remember, it was like 60% was being refreshed once in every 128 milliseconds, and the 40% were being refreshed twice. So it's the same story here again. I just look at every 128 milliseconds, 10% of the rows are refreshed twice, and 90% is refreshed once. So when we just add them up their costs, we see that the bank is occupied for 0.22 milliseconds for every refresh. And this every refresh happens at every 128 milliseconds, so refresh overhead is this number here. Okay? So this was our baseline and the answer of this question. And the last part of the question is here. So here we are merging these, like on top of the baseline, we want to add partial refreshes. And in the partial refreshes, we have another plot here. So here we have two refresh intervals, one for 64 milliseconds, the other one for 128 milliseconds. And the y-axis is the same as before. So here you can see that when we add all these up, it goes to 100%. So this is the distribution. And okay, so let's start with this 128 millisecond ones. So here I refresh all these rows. I mean this 20%, the 65%, and 5% at every 128 milliseconds, right? And for this 20%, it's always full refresh. And for this one, it's one full refresh, one partial refresh. And for this one, it's 3 partial refreshes and 1 full refresh. And then for the 10% of them, I need to refresh them at every 64 milliseconds. And it should be one full refresh, one partial refresh. So just by following the same method, we can see that at every, so you can choose whatever value you want here. I just choose 4 times 128 milliseconds because it makes the calculation much easier. You can go for another value. It's up to you. And you can see that for every 20% of the rows, we refresh this 4 times. And then these 4 refreshes, all of them are full refreshes, and none of them are partial refreshes. And for 10%, I refresh them 8 times because this was 64 milliseconds in refresh interval. And half of them, I mean the 4 of them full refresh, 4 of them are partial refresh. And you just go like this. And then when you just convert these texts to mathematical representations, then you get these equations here. When you just add them up, you can easily reach to at least up to this point. You should be able to reach very easily. It's very straightforward math. And then, yeah, if you compute more, you can get these results. But you can just take this equation and say it X or, I don't know, A, something like that, and then compute the rest of the thing just by using that parameter. And as mentioned earlier, you don't have to compute the final exact value in the exams unless it's explicitly stated in the question. And you need to answer all the questions you see in the text, and you need to show how you get those numbers. We should just see your method, how to retrieve them. Okay, so this was the DRAM refresh question. Do you have any questions?
Yeah, let's start with some new RowHammer problems. Yes, here, yeah, we should have thought about, yeah, what and how we consider when we develop the RowHammer mitigations. Yeah, so the problem, yeah, let's read the problem. So one researcher rigorously investigated the relationship between the DRAM refresh rate and RowHammer introduced errors using real DRAM modules from 3 major memory manufacturers. And yeah, they used the most RowHammer vulnerable modules in each DRAM manufacturer. So yeah, this graph is the worst case scenarios. So yeah, very conservative manner. And as shown in this figure, we can achieve an effectively zero probability of RowHammer induced errors when we reduce the refresh interval to 8 milliseconds. So here is 16 millisecond, and before we reduce the refresh interval to 8 milliseconds, yeah, the errors of all modules are close to 0. Yeah, so this is because the probability of RowHammer induced error becomes less than that of a random DRAM circuit fault. Okay, and based on this, as a leading computer architect of a company, you are asked to design an efficient RowHammer mitigation technique. Yeah, but your junior engineer suggests a very naive, but an immediate mitigation technique which reduces the refresh interval from the default value 16.4 millisecond to 8 millisecond. And this is very straightforward that the bank utilization and the energy consumption will increase, linearly increase along the number of refresh requests we should perform in a same time interval. So so E and U is linearly increased for number of number of refreshes, and if we reduce the refresh interval, we increase this. So we can easily know the energy consumption and the bank utilization should be increased 8 times, both. Make sense? Yeah. And the next question is the feasibility of this approach. Fortunately, okay. So the recent DRAM manufacturer successfully released a higher capacity version of the same DRAM module. And you figured out that with the rigorous reverse engineering, they only double the number of rows in a bank and the number of banks in a module without changing any other aspects. So in this case, in this question, asking how the bank utilization will increase along these changes, and if the number of banks and number of rows per bank increase 4 times, then how it should be changed. So with just 2x increase, it is still applicable. And so here the current bank utilization is 0.05, 5%. So in our calculation, when when it decreased the refresh interval to 8 milliseconds, yeah, the bank utilization increased 8 times. Yeah, and yeah, here is some fake information, right? So the bank utilization does not affect it to increase of the number of banks in a module. So we just multiply 2, which means double the number of rows in a bank. And yeah, this is 80%. And yeah, so this is possible. So in terms of RowHammer protection, yeah, because we can refresh every rows within every 8 milliseconds, so we can protect against the RowHammer attacks. But yeah, it is quite impractical because the most of bank utilization is consumed to the refresh. And yeah, if the number of rows and number of banks increases 4x, yeah, and it is impossible to protect. Actually, yeah, it is impossible to reduce the refresh interval to 8 milliseconds because bank utilization becomes larger than 1. It means that even though we spend all the time for refreshes, we cannot refresh every rows in a module. Yeah, and it means we cannot apply this approach if the number of rows and number of banks and number of rows increase to 4x. Okay, so this approach, this reducing refresh interval is not feasible when DRAM scales out. So we should think about another approach. So due to significant overhead of reducing the refresh interval, you can decide to find another RowHammer mitigation technique with a lower overhead. So the junior engineer proposed another technique which is counter-based. So in this approach, the memory controller maintains a counter for each row R, which increments when an adjacent row is activated. So note that there can be some multiple approaches using counter to mitigate the RowHammer effect. For example, we can count the number of activation of a row, and if it exceeds the threshold value, we can activate the adjacent rows of the activated row, right? But here, they did not choose that approach, but instead they count the adjacent rows activation, and if it exceeds the threshold value, it refresh the victim row, potential victim row. So there are many pros and cons for each approaches. Okay. So the question is, so here are a bunch of information about your DRAM modules for now. So here is interface generation and cost latency and TRCD, a bunch of information. And the question is asking, are the given specification enough to implement the proposed approach? And I think it is quite open question, but this question is asking the essential information to implement this techniques. So what I intended is we should know if we do something with about adjacent row, we should know where is the adjacent rows, right? But as we covered in our classes, a DRAM manufacturer does not open it. it is normally confidential. So yeah, we should know the exact mapping between raw addresses and physical rows. In this case, yeah. Anyway, yeah. Suppose that, all the necessary specification, means the exact mapping between the raw address and physical rows. For implementing the proposed approaches are known, and calculate the maximum value of t, so the threshold value that can guarantee the same level of security against the RowHammer attacks over when adopting 8 millisecond refresh intervals. Yeah, the reducing the refresh interval means that it limits the number of activation within the consecutive refresh, right? So the maximum we can, if we reduce the refresh interval, we can limit the number of activations, number of hammering, because the activation, the hammering method is now activation. We can limit the maximum number of activations. So so actually, to calculate this very optimally, we should know, we better to know the possible number of possible activations within 8 milliseconds. But in theory, we can the maximum bound of the number of activations in 8 milliseconds with this low cycle latency, which is the sum of TRAS plus TRP. And so it means total about 65,000 activations can be possible in single 8 milliseconds. So if we set the threshold value as this value, then we can at least guarantee the same level of security against the RowHammer attack over with the 8 millisecond refresh intervals. Make sense? And so the next question is asking the number of bits required for maintaining counters in each memory controller, and it's very easy actually. With B, let B is the number of bits. We can maintain these many informations, and so it should be larger than t, and definitely we need to calculate the maximum value. So minimum value of this. And we can simply know. With this some logarithm method, and this t is 18. So so for more correct more correct equation inequality is this. And with this value, we can simply calculate the number of bits required for the counters. And it can be increased 36 millibits if the number of rows and number of banks are doubled. Okay. So the reason why we use the maximum threshold value is to minimize the performance over it. So this question asking the goal of that we use the maximum value of maximum threshold value. So obviously we can reduce the size of counter in each memory controller if we use a smaller value t. For example, if we use just a threshold value as 1, of 1, then the size of counters definitely should be increased a lot, but we need to refresh adjacent row whenever we activate our row. Twice or something. So the performance and energy overhead from unnecessary activation or refreshes is the cost of using a smaller threshold values. And the final question, you recall para, which is proposed in the first RowHammer paper. And here is some description of how para works. And I suppose you are already aware of it. So the key question is, we know the error for para. So error rate of para experiencing sorry for that. We know the probability for para to experience an error in 16.4 millisecond, which is very small. And let this as what? P64 millisecond. When the parameter, the probability parameter in para technique is just 0.001. And this is the worst operating condition. And the question is asking, how we can estimate the probability of experiencing an error in 1 year based on this value. So the problem. So this is the probability of experiencing an error for 64 milliseconds, and the question is to get this, which is the probability of experiencing an error for para in a year. Then we can consider a year as a sequence of independent 64 millisecond time intervals, and the number of 64 millisecond time intervals like this. Let's say this is this is m, and we can the number of errors in a year can be modeled as a random variable which follows a binomial distribution. With the parameters n is the number of 64 milliseconds time interval, and the probability is this value. And therefore, if the probability that at least one error occurs in a year can be calculated, the variable x, the probability of that variable x is equal or larger than 1, larger than or equal to 1. And this is because x is discrete value, we can simply know is like this. And in binomial distribution, the probability of the event never occurs is simply just multiply n times, and the final answer should be like this. And this can be, fortunately, this can be calculated with the calculator in your PC maybe. So, but it should be fine. Just leave this form in exam or homework as well. But and definitely if you use some approximation or some inequality for example, Markov inequality, because this variable x should be this variable x, and the probability should be larger than, so positive value. Then we can use Markov inequality to bound the maximum value, or and this binomial distribution with very large trials and very small probability, then we can approximate the distribution to Poisson distributions. So if you use that and refer to that reasoning, then it should not a problem in this question. You will get all the credit. Okay, any questions?
This question is question 4.1 in your homework too, but it also was an exam question, midterm exam question, actually in fall 2017. I'm not going to read it completely, and actually I'm not going to solve it. I will essentially read the solution given the amount of time that we have. So in this question, what we are going to work with is with the Bitmap indices, which is one of the benchmarks that is used in the AMBIT paper. You might remember it. And essentially here, what we have is a database, and we want to query this database to find a solution, or an answer to the question, how many unique users were active every week for the past W weeks? So the way that this information is represented in the database is by using individual bits. Each individual bit in a row identifies one particular user, and we are going to have all the bits corresponding to different weeks in different rows. That's essentially what the question says. We have to compare two possible implementations. One of them is CPU-based. The other one is AMBIT-based. In the case of the CPU-based, what we are said here is that we need to make very basic or simple assumptions on how to compute the throughput of this implementation, because this is a very memory-bound operation. The only thing that we are going to take into account is the memory bandwidth. So essentially, this will be the cost of bringing the data from memory to the CPU, and then this computation, which is very little one, it's essentially hidden by all this data movement. And in the case of the AMBIT-based implementation, we have an accumulation row and we have an operand row. So in the accumulation row, we are going to have the partial results until we go over all the weeks, and then we will have the final results for every single user here in the accumulation row. And to the operand row, we need to move the row corresponding to the week that we are evaluating. Another thing that we are set here is that we are given two latencies. The first one is TRC, which is the latency of a row clone operation, because whatever row representing the activeness in a single week, we will have to move it to the operand row. And then we have this T-AND, which is the latency of an AND operation, because in order to merge all the results from all the weeks for the different users, the operation that we do here is an AND, a bitwise AND. So first question is, what's the total number of DRAM rows that are occupied by U users and W weeks? So first thing to keep in mind, to take into account, is what's the size of the DRAM row. It is 8 kilobytes in this example. So in every row, what we have is 64K bits. So we can fit 64K users in every row. If the number of users is U, we will need all this number of rows to keep all the users for a single week. Because we have W weeks to evaluate, this is a total number of rows. The calculation of the throughput is quite simple, as you will see. First of all, we are going to evaluate the throughput on the Ambit-based implementation. In order to calculate the throughput, what we do is essentially, because it's the throughput in users per unit of time, in users per second. So what we will have is a fraction. In the numerator, we will have U, which is the number of users. In the denominator, we will have the total time that we need to compute for these U users and W weeks, right? So this total time is going to be the total time for all the AND operations plus the final bit count that the question says that it's computed on the CPU, because Ambit doesn't include bit count operations. So if you look at this AND total, what we have here is exactly the number of rows that we need to operate on, which is the solution of part A, times the total latency for each of these rows, which is the latency of moving the row to the opener row plus the latency of ANDing the row with the accumulation row. And finally, for the bit count, the only thing that we need to do is moving the bits corresponding to the U users at a certain rate, and this rate is the bandwidth, which is X. So this gives us this amount of seconds. That was for the Ambit-based implementation. For the CPU-based implementation, computation is even simpler. Why is that? Because we only need to think about what's the amount of information that we need to move, all these bits, divided by 8, because it's number of bytes, divided by the total bandwidth, which is X bytes per second or gigabytes per second or whatever. Okay? And finally, last part, what's the maximum W for the CPU implementation to be faster than the Ambit-based implementation? It's very reasonable to ask ourselves this question. Why is that? Because Ambit essentially is going to be efficient if we are operating on entire rows, right? If we are operating only on very few users, let's say 5 users, it doesn't make sense to compute using the Ambit engine, right? It would be wasting a lot of energy and potential throughput there. So as you can see, what we do is comparing these two times TCPU and the total time for the Ambit implementation, which is on the right part of this equation, and from here we can obtain W, which is the maximum number of weeks, in this case, for which the CPU implementation will be faster. Okay?
Okay, the next question is from the second homework. This is question 5 from homework 2. Okay, so it covers caching and processing in memory. And the question is like this. So it defines 2 arrays, 2 integer arrays, A and B, and they have elements of size 4 bytes. And here you can see the base addresses of A and the base address of B. And here we have a piece of assembly code. So I won't go through this code now, but instead I will directly jump to the question. I think it will be easier if you do so too, because first trying to understand the code might be more difficult if you don't know what to answer. Okay, it makes more sense to first read the question. So here it further says that we have a single core processor that executes this code, and this processor does not have any caches. The load store instructions access directly the main memory, and then we have a fixed latency of 50 cycles for both read and write operations, and those are serialized. So it's pretty easy so far, right? Everything is serial. We have fixed latency, no cache, and memory requests cannot be overlapped. Okay, so everything is pretty straightforward, and then the execution time of non-memory access instructions is 0. So here in this code, we will take into account only memory accesses. Okay, and then the question is, what's the execution time of this piece of code on this processor without any caches and 50-cycle main memory latency? So now if we look at the code, we see that we have two loops named outer loop and inner loop. And if you check here, what is the condition for the branching against the inner loop? It is basically this, like this case where R4, register 4 is not equal to 2. So here we set R4 to 0 at the beginning of the outer loop, and here we increment it, right? Anywhere else in the code, we don't modify R4. So basically, this will mean the inner loop will execute once. At the end of the first iteration, we will increment R4, and here we will compare 1 against 2. And since 1 is not equal to 2, we will need to repeat the inner loop one more time, and then exit. Okay, so the inner loop will execute 2 times. And then the outer loop will execute how many times? So here it will branch on R3 equals 16. And then we increment R3 here, and we set R3 at the beginning of the program. So this basically means the outer loop will iterate 16 times. And in each outer loop iteration, we will do the inner loop twice. Okay, in total, we have 32 inner loop iterations. Okay, so inside the inner loop, we have 2 loads. Let me use a different color here. So we have 2 loads. And at the end of the outer loop, we have a store here. Since we execute this twice, the inner loop twice, we'll have 2 loads. 2 loads per iteration and 4 loads per outer loop iteration, and then followed by 1 store. And then we will repeat those 5 memory accesses 16 times. Okay, and then the answer of this first part is pretty easy, right? So we have 16 outer loop iterations. We do 5 accesses, and each access takes 50 nanoseconds. And then if you do the math here, it's basically, this is cycles, not nanoseconds. And the answer will be 4,000 cycles. Okay, this part is pretty easy, right? Any questions on this? Okay, so now it becomes a bit more complicated because we add a 128-byte private cache. And here are the properties of this cache. So the cache block size is 8 bytes. Okay, so based on this information, we can directly see that we can fit 2 elements, right, into one cache block. This is important. And then the cache is direct mapped. And access to the cache takes 5 cycles. And on a miss, we go to the main memory and then again pay the 50-cycle latency. And the question is the same. So if you have this cache, what will be the execution time of this code here? Okay, so this part is a bit more tricky. First, we need to understand exactly where in this cache elements of A and B will map. So we know that the cache is direct mapped, and it has 128-byte capacity in total, and each cache block is 8 bytes. So basically, here we'll have 16 entries that are direct mapped, right? So I find it basically by dividing 128 by 8. So it will look something like this. So this is the first set or entry, and then second and third, and we have this until 15, right? So then if we look at the base addresses here to determine where in this cache the first elements of A and B will map, so we can first basically find out which bits of the address tells us the entry in the cache to access, right? And then since we have 128 bytes here, the last 8 bits of the address will we'll have to do something with the cache, right? So basically, since we have 8-byte blocks, the last 3 bits of the address will be the offset, right? So which byte within the cache block is addressed. So like those 3 bits, least significant 3 bits will indicate that. And then, this is 4. And then the next 4 bits here of the address will tell us which entry of the cache that address is targeting. So if we convert this hex number to binary, we will see that we have like a bunch of zeros here. So we'll have 12 zeros, and then here we'll have 1. Right, so we can easily see that here the first element of address A will go to the first entry of the cache because all least significant 7 bits are 0. And so it's the same for B, for base address B. Again, here we have 12 zeros, right? So this basically tells us that the first elements of A and B will conflict on the first cache line, on the first entry over here. So basically, when we access A0, when we want to access A0, it will bring A0 and A1 to this position. And then if we want to access B0, it will evict A0 and then put B0 and B1. Okay? So based on this, we can now start understanding what this access pattern looks like. So here in this code, we see that R1 is the base address of A, and then R2 is base address of B. So this first load is targeting some element of A, and then the second one is targeting an element of B. So here we use R5 to iterate over this array, and here we use R4. So R5 is calculated by adding R3 and R4. So we already have some understanding about R3 and R4. R4 is basically the counter that we modify inside the inner loop, right? So it gets either 0 or 1 as a value. And then R3 is the outer loop iterator, which gets values from 0 up to 15. And so basically what will happen here is we will first access A0, right? Because initially R5 will be 0 plus 0. And then in the next iteration of the inner loop, we'll access A1. And for B, we'll access B0, and then B1. So those will be the locations we will touch in the first 2 iterations of the inner loop. And then here, for the store, it is R1 plus R3. And R3 is our outer loop iterator. So it will be basically the base address of A plus R3, which initially will be A0. Okay, and in the next iteration, what will happen is we first, after we complete the first outer loop iteration, we will go back here, we will reset R4 to 0, and then we will calculate R5 as 1, because we incremented the outer loop iterator plus 0, so we'll have 1 here, and then we'll access A1 first, and then we'll access A2. Okay, but for B, nothing changed. We'll again access the first element of B, B0, and then B1. Is that clear? So basically, it goes like this: A0, or let me put it that way. So we touch 0, element 0 of A, and then 1. And then 1 again, and then 2, and then 2 and 3. It goes this way. But for B, we basically repeatedly access elements 1 and 0 and 1. Okay, so here, it's not only important to determine exactly which locations we access, but also the order of those accesses is important because they are conflicting in the cache. So in addition to compulsory misses that we'll have, we'll also have conflict misses in the cache, right? And let me show that too. Okay, so in the first outer loop iteration, those will be the addresses that we will access, right? So we will first access A0, and then we'll access B0, and then A1, and then B1. And then finally, we will do A0 again to store the value that we calculate. So initially, the cache is empty. We will get a cache miss. So this is a compulsory miss for A0. And then same for B0. This is the first time we access B0. But here, an important point is that when we access B0, it will evict A0 because they map to the same cache entry. Right? Okay. And then we access A1 again. So A1 was brought by when accessing A0 because they map to the same cache block, right? So we sort of prefetch it. But since B0 evicts that block, at this point we will not have A1 in cache. But if we didn't have this access to B0 here, then in that case, the second access would have been a hit. Okay, and then here the same thing happens. A1 discards B0 and B1 from the cache, and then we get another miss here. And then the same thing happens, and then we again get a miss. So this is what happens in the first iteration. All accesses miss in the cache. And the second outer loop iteration, so as I said, we increment A in each iteration, but we keep accesses to be the same. Okay. And then now, so the last element we accessed was A0, which brought A0 and A1 to the first cache line. So this is a hit, right? And then B0, access to B0 again, this is not in the cache, was evicted, and this discards A1 and A0. So then we access A2. So this is the first time we touch that cache block. So this will be compulsory miss. And then B1 is in the cache because A2 maps to the next entry, right? So A2 will be placed here together with A3. So B0 will remain in the first cache line. So we'll have a hit here. And then since A1 is not in the first cache line, we'll get a miss. Okay. Nice. Okay, I'm going to now quickly go through some other iterations just to show you the hit and miss pattern that we'll eventually get. So A3, B1, A2. So in this iteration, what will happen is we already have A2 in the cache. Nobody evicted it. This is a hit. Do we have B0? No, because last time we accessed A1, which evicted B0. This is a miss. This is a hit. A3 came together with A2. And then this is a hit because B0 brought the cache line. And then A2 is hit again. Okay, so this is what happens in the third iteration. And I think I'm going to show 2 more iterations. A4, B1, A3. We accessed A3 before. This is a hit. We have still B0 in the cache. So if it's difficult for you to follow what's in the cache, what's not in the cache, you can use this and then basically write it here, what is currently in the cache, and then when you evict something, you can just modify it. But I'm not doing it just because to save some time. But in the exam, if you think you can make a mistake, you can do it more safely. Okay, A4 is a new cache block that we'll need to access. So here we'll have a miss, and then for B1 we'll have a hit. And for A3, we will have a hit. So here, at this point, you see that starting with this third iteration, actually, we always get, starting with this iteration, we'll always get hits for elements of B, because they won't be evicted, we don't access A1 and A0 in those iterations. And we will also get always hit for A3 because we will first access it here in the beginning of the iteration, and then B won't conflict with it. And every second iteration, we will get a miss on this element here. So let me execute one more iteration. So here we will do access to A4, B0, A5, B1, and A4. So what will happen in this case is we already have A4 in the cache, so this will be a hit, this will be a hit, this will be a hit because A5 came with A4, this will be a hit, and this is also a hit. Okay, and in the next iteration, we will basically have hit to A5, hit to B0, miss to A6, it's a new cache line, and then hit again, hit again. Okay, so starting from this, starting from this iteration here, we will have 1 miss and 0 misses, right? And those will interleave. 1 miss, 0 miss. We know that in total we have 16 iterations, so we will end with what? With 1 miss, right? Here. And here we have 1 miss for this iteration, 3 misses, and 5 misses. So if we add everything together, it is 8 misses here, 8 misses plus how many? So it's 13, right? But 6, 7, right? So we'll have 7 more misses here. Sorry? 13. Yeah, it's 7, isn't it? Oh, yeah, okay. Sorry. This is 9. Okay. I was like, okay. Yeah, so in total we have 16 miss. And then the rest will be hit. So like it's quite easy to calculate how many accesses we have here in total, right? So it's like 16 multiplied by 5. We have 80 accesses in total. 16 of them will be misses, and the rest is hits, right? We have 64 hits and 16 misses. So based on that, you just do the math. You have the number for, so it takes 5 cycles to serve a request from the cache and 50 cycles otherwise. You do the math, and then you end up with the execution time. Okay? Yeah? Yeah. Yeah, so I think, so I don't remember what we did in the question, but it's not like very explicitly stated what happens exactly, but in the question, so it says, on a miss, the main memory is accessed, and the access fills an 8-byte cache line in 50 cycles. So that will mean you should also apply another 5 cycles to bring the data from the cache to the processor, right? So it should be 55 cycles in total for a miss. So what we used here is so here in the solution, apparently we don't take that into account, so we just use 50. I mean, ideally this should be clearly specified in the exam question, okay? So it will be like all the way to the CPU, you bring the data from the main memory in X cycles, or you bring it only to the cache in X cycles, and then you still have to pay the hit latency. Okay, it will be stated clearly in the exam. Okay, so that was part B. Any other questions? Yes?
I think this is outside the scope of this problem, but for like store instructions, normally we have to consider like the right group.
Right. Yeah, exactly. Yeah, here it's very simple in this question, yes. Okay. I had a blank page here to use, but yes.
But here you're assuming that the memory is word addressable.
No, it's byte addressable.
But if you see in the code, for example, if you assume R2 is 1 and R4 is 1000, 8000, the address will be 8001. Whereas to access B of element 1, it should be 8004.
Oh, okay.
So yeah, it's
Okay, yeah. So here, we also have a mistake in the code, I think. Yeah, I agree with that. So here we should increment with,
because it's different. If you
not by 1, by 4, basically.
Yeah.
Yeah. Okay. Okay. Yeah.
Can you just re-explain how you calculate the offset?
Like you're asking about like which elements in the code we access?
Many times in the exercises,
Mhm.
I calculate the offset, and I'm not really sure about what I do.
Like this part here?
Yeah.
Okay. So here, the overall cache size is 128 bytes, right? So this means we'll have 8 bits to determine like where in the cache data will map, right? So like for example here, we know that a cache block has 8 bytes. So that will mean we will need to use 3 bits to determine the position, the byte position in that cache block, right? So you have 8 different bytes. You address 8 with 3 bits.
So you say that we try to address 1 byte.
Yes.
Okay.
Yeah.
How do you know you're trying to address 1 byte?
So if it's not stated otherwise, you should always assume byte addressable memory. So like in lectures, like everything we do is byte addressable. If it's not byte addressable, it will say that in the question. So it's like I think it's sometimes difficult to think about like things that we have to define in the question. So like we usually end up having such issues. Like you can always find something that people like design differently in their systems, but like I don't know any system that uses anything else than byte addressing, like in the real systems. And this is also what we use mostly in our questions and in the lectures. It's always byte addressable. Yeah. Yeah. I think so, yeah. As long as what you're doing is reasonable, and if there's like any issue or anything not specified in the question, and then you solve it based on your assumptions and everything is reasonable, I think it's good. Okay.
The offset will be always 3, except if we...
So the least So the least significant bits is basically the offset, right? So typically cache lines are 64 bytes. So in that case, you'll have 8 bits that you use. Sorry, not 8. Yeah, you have 6 bits as an offset in that case.
yeah, sorry.
Yeah. I mean, I don't want to confuse you further, but you can think of it as an address of the byte inside the cache block, right? That's what we call offset. Okay. I will continue with the part C. So here, This part is very similar to the first part, which was very easy, where we had a processor without any caches, and we directly accessed the main memory with 50 cycles. But here, instead, it says that we have a near memory processor, which has only 10-cycle access latency to the data in the main memory. And we don't have caches again. So this is exact same computation that we need, calculation we need to do for part A here, except we change 50 with 10. And then you end up with 800 cycles of execution time. Okay, I think that was very easy. And then part D is, let me read this quickly. Your friend, oh my God, we have too many mistakes in this question. Your friend now suggests that by changing the cache capacity of the single-core processor in part B, she could provide as good performance as a system that utilizes memory processing in memory unit. Is she correct? What is the minimum capacity required for the cache? Blah, blah, blah. So here, she's not correct because no matter how big is the cache, no matter how many entries we have here, we will have conflicts in the cache line 0 here, and then it will increase the execution time a lot, so we can never complete the program in 800 cycles, even if the rest of the accesses are always hit. And we also have compulsory misses. So if you do the math, if you try to calculate the best case here, you will see that you cannot do better than this over here. So basically what will happen is, by just increasing the cache size, you'll only be able to turn those misses here to hits, right? But you will have the rest of the misses here, which are the compulsory misses. Yeah. Mm-hmm.
Does it say that we cannot increase the size of one block? Then we will only have two misses, right?
Yeah. So here it is just increasing the cache capacity by increasing the number of entries. You cannot increase the cache size by increasing the cache block, so it has like different consequences, right? As you know, because like increasing the cache block size will also need to potentially increase the number of bytes you fetch from the memory for each request, and then you may also need to maintain some metadata to know like which parts of that big cache block you have brought to the cache. So it changes the design completely. So here, and in this part, you just change the cache by increasing the number of entries you have in the cache. And in the second part here, or in the fifth part, in part E, it asks you how you can change the cache design while keeping the capacity the same, or like also increasing the capacity potentially, how you can change it to improve the performance of the design with cache. And here the answer will be basically, so what was the problem here with the previous cache design? We had those conflict misses, right? So we have to have a design that will avoid the conflict misses. And the best thing you can do here is just to turn this cache to a design where you have two ways, right? In that case, you can keep both B0, B1, and A0 and 1 together in the cache, and you'll avoid all conflict misses. And you don't have to increase the size of the cache. It's not helping because you don't have temporal locality here, right? You only have temporal locality to elements of B and some elements of A. Actually, you have some, but you don't need a very big cache, right? So only like having a cache with like 16 entries, for example, is like good enough. So you don't have to increase that. Okay. Yeah, I think I agree. That's a different thing you can do to improve performance. So basically, in that case, you will not only turn those conflict misses to hits, but also some of the compulsory misses because you will prefetch the data. Yeah. Yeah, so this is like sort of a more open-ended answer, basically. So you have like two options at least. You may also come up with some different change in the design to improve performance. So in such cases, you basically have to list everything that you can think about to improve performance or, yeah. Okay, any other questions? Yeah, okay, I agree with that.
And it was so many times that I'm facing a question and I don't really understand what's here.
Yeah, so as I said, in the final exam, it should be much more clearly defined. Yeah. Okay. Then we will continue with the next question.
So this is a very interesting question, hopefully. And it's related to the lecture number 5 about accelerating genome analysis. And in this question, you are asked to solve 3 parts about finding the added distance between 2 strings. So how many of you still remember this lecture? Okay, very good. All right, so edit distance is the minimum number of edit operations that you need to do so that one of the sequences will be similar to the other one. So those edit operations are 3 types, can be substitution, deletion, or insertion. And basically, you could follow the dynamic programming algorithm where you design it yourself or you solve it, you calculate it for each of those 2 sequences. Or you could, if you are smart enough, trying to find the number of operations that you need to do so that one of those 2 sequences will be similar or exactly typical to the next one. So let's see this example. You have Montag and Donnerstag. Is that correct? Okay. So apparently, you have the tag part is common between the 2 sequences. So that gives you 3 matches. And you have another 7 characters that don't exactly match. So you have the S, R, and so on. So anyway, so for those kind of questions, you need to start from the first character, very first character, and you move all the way until the end, okay? So if you try to do this way, that will give you some incorrect answer. And you need to note that, though you might find a way that you could make this sequence similar to the other one, but might not be the minimum, and that will lead to a wrong answer, okay? So you have to be very careful about those. And that's why we use dynamic programming algorithm to solve such kind of questions, so that we can enumerate all kind of prefixes. Oops, it's too late. Okay, can everyone see it? Okay. Okay, so in dynamic programming algorithms, we're trying to enumerate all prefixes and see which one gives you the minimum number of edit operations. So how we do it, let's try again. So you have the, let's type it again, one tag. And let's start with the D. Does D match here? No. Does it match the next few characters? No. So probably this should be substitution, okay? Now this is one operation. Now we have the O. Does O match the corresponding next character in the second sequence? Yes. Okay, that's perfect. So we have an exact match here. And then we move to the N, which is exact match. And then, unfortunately, we have another N. Does it match? No. Does it match with the previous character? Yes. So apparently you have an alternative solution here where you could have an exact match here, right? So you could delete this N or the next N, right? Both of them correct, by the way. So you could do that. And now what's the next? It's E. Does E match the corresponding one, which is A? No. Does it match with the next one or the previous one or the few next, few previous? No. Now, how few you should go? How far you should go? Probably if the two sequences are short, then you shouldn't move more than 2 or 3 steps around that. But sometimes we call it a banded edit distance, where we restrict the number of steps you could move forward or backward. And in this banded, we give you a threshold, 2 or 3. So that will restrict you moving how many steps right or left. Anyway, so and apparently here we have another deletion. By the way, if it is a deleted character from this sequence, it's same as if you insert it in the other sequence. So deletion or insertion, same answer, okay? Now, what's next? So we have the R, same story. We need to delete it. And we have the S, and then we have the tag. So how many edit operations we did here? We did 5. Five steps, 5 deletions from here. We have the 1, 2, and we have another 3 here. Or you could do 5 insertions to the other sequence. Okay? Any question? Yes? So if you are banded with some limited number of edits, yeah, then probably this exceeds the threshold that we set in advance, then probably you don't need to continue. Because anyway, what does mean banded is you have the dynamic programming table, right? You have some diagonals. So banded mean number of diagonals that are next to the main diagonal. So if you have the main diagonal, which is the one in the middle, now the banded mean if it is 3, then you are allowed to construct only 3 diagonals next to the main diagonal. Likewise, you can construct another 3 here. So probably if you have 5 edits, for example, then your computation need to be exceed this limit, which is the band you have, which is 3 and 3, plus the main diagonal, 7 diagonals you have. So you cannot compute it using this dynamic programming table if it is banded. Okay? So probably you need to stop computing after you exceed that threshold. Then you can say that those 2 sequences has an edit distance more than the threshold, which is 3 or 4. Okay? So now let's go to the second. So let's try with the S. S doesn't match, apparently. Does it match with the next? No. Next, no. So apparently we need to delete this character from here. Then we have the A, same story, no. Then we have the M. We need to delete it. So we don't need to delete it, actually, here. Maybe substitute it. It's more accurate. Why is that? Because we want to keep it the same length. Okay? So we have the S and then the tag. So if we substitute the S with the I, M with the E, A with the R, and S with the F, then it will be exactly match, right? So how many edit operations did we do here? So we said 4, right? Because we need to substitute these. Okay. Now, we need to have this compared with a null sequence of empty characters. So apparently either you add all of these characters to the second sequence or you deleted them from the other one. So how many operations do we need? Equal to the number of characters here. Okay? All right. Now, why we explain the lecture about edit distance or other metrics that we measure the similarity or the difference between 2 strings? So we need that in genome analysis, for example, to tell us how many differences between your genome and the other genome, which could be a reference or somebody else in your family, for example. So here's an example of how we do that. You are given those 5 reads, and at each read, we chop it into 3 k-mers, and for simplicity, I give you the delimiter here, which is underscore, that divide the k-mers of a single read. So k-mer, the k here is the length of this substring or subsequence. So here we have the k-mer length is 5, so k is 5. So how many k-mers we have per read? 3. So we said in the question that this is a hash-based read mapper. What does that mean? Meaning that the first step in read mapping or in genome analysis, the indexing part will be based on a hash table. Okay? This is what does mean hash-based read mapper. That's why you are given this hash table, and you are given a bunch of reads. You need to map those to the hash table and start extracting some locations from the reference genome. So we are going to use the very basics method of doing that without any filtering, without any advanced mechanism in the first part of the question, which is this. Can you see it? Okay. So here you are asked that how many times you are going to apply this edit distance function. So how we do that basically is picking the first k-mer from the first read and go to the hash table. Does that k-mer exist in the hash table? If yes, then we extract all the corresponding locations. And at each location, we apply or we perform the edit distance function. So we pick the first k-mer, which is A's, 5 A's, which is here. How many locations? We have 6 locations. So at each location, we are going to check one by one the edit distance between this read and the reference genome at this location, so starting from 10 all the way to the same length of this, which is 15. So we start from 10 to the position 35, or 25, sorry. And we do the same thing with the other locations. Okay? So we pick from the reference at this location, and we compare it with the read for edit distance. Okay, so how many times we do that? So the first one here, how many times occurred? So 6 plus AACs, which is here 3 times, plus the 5Gs 3 times. And now the second read, 4 A's plus T, which is 2 times. And then double G, double C, T, which is 5 times, plus A's, again 6 times. Now the third one, AETs. So I'm going to do some cheating here and copy the answer because it's repeating itself, right? Do you want me to continue? You just need to count how many times you get the location basically for this. So let's have it here, 2 plus 0 plus 0, and then 3 plus 2 plus 5, and then 6 plus 5 plus 3, and that will give you 51 locations need to be examined for edit distance. Okay? Yeah.
I just wanted to say that when I did it, because you can call edit distance with not the same size of the string you put as input.
Uh-huh.
So I chose to put 5 characters as input and to only call the edit distance on the ones that you didn't know that they matched. So for each read, you only call edit distance twice, but with parameter of size 5.
Oh, wow. Okay. Why would you do that?
Because it was not specified. And it actually, it's quicker.
Okay. So basically, you already know from the hash table that the k-mer is exactly matched, right? So now the question, where to perform the edit distance. So you already know that those 5 characters exactly matching with the reference, right? Now, whether you go to the next few characters or the previous characters in relationship with this k-mer, right? Now, okay. Yeah, if you assume so, nobody can argue with you, right? Unless it's specified in the question. But that's interesting. Okay. So now the second part, trying to do some sort of smart way of doing the comparison between the strings. So they ask you to use adjacency filtering. adjacency filtering mean you need to relate the k-mers together coming from one read. So you don't need to perform a distance per each k-mer. So meaning that here the distance between, so to call a k-mer adjacent to the next one, the distance between two k-mers should be 0. This is how they define it here. You can see they said if the first k-mer happening at the location x, then the second one should be at x plus k, which is 5. So they should really be next to each other. The distance between the k-mers should be 0. Okay?
Why would you call it a distance if you know it's 0?
Yeah, you can consider it as Hamming distance, for example, or at a distance 0.
So why do you call it if you know that it's...
So this is just to simplify the question so that you don't need to calculate the distance and subtract the... For example, if we allow for five steps between two k-mers, then that's considering 0, 1, 2, 3, 4, and 5. So you need to deduct all those possible values from a location such that you're on safe side, right? So this will complicate the calculation for your side, right? So anyway, if you want to assume that there's a single step between the k-mers, here the assumption is not valid, right? Because it's already given the question that the step is 0. So you cannot assume something else. The distance between the two k-mers should be 0. But the answer is not 0. Let's see what the answer is. Okay, so how we solve this question? Again, exactly same way, but we need to relate the two k-mers together, or the three k-mers coming from the same read. How we do that? Let's go to the first read, first k-mer. Then the 5 A's. How many times happening here? 6 times. Okay. Now, we shouldn't stop and perform at the distance. We need to proceed to the second k-mer, which is 4 A's and C. How many times happening? 3 times. Okay. Now, which one of these locations is adjacent to these 6 locations? How we do that? Now, the 15 is really next to the 10. Why is that? Because the k-mer size is 5. If the k-mer length is 4, then the distance between the two k-mers is 1, right? So meaning that this location is adjacent to the 10. Now, 610 is not adjacent to any of those, right?
We don't see on the...
Oops. Okay. Yeah, thank you. So the 15 is adjacent to 10, right? You agree on that. And the 610 is not adjacent to any of these. Why is that? If you add 5 to any of those, won't give you any of these locations. So the same thing for 720 is apart from 710 by 10 steps. So this is not valid based on the definition given the question. Okay? So none of these valid. Now we are having only single location coming from this. Now it's based on the third k-mer. If it exists adjacent to these two, or at least to this AAC, then we are going to perform at a distance here. Yeah, I know it's stupid to perform at a distance here. Why is that? Because it's already exactly matching the 3 k-mers. So now let's see the 5 G's here. The 20. Is 20 next to 15? Yes, given that the k-mer length is 5. So we are going to perform at a distance here once for this read. How about the others? 600, 700, they are not adjacent to 15. So we just ignore them. Now we do exactly the same thing. Let's repeat for the second read, for example. So we have the 4 A's and single T, which is here, and we have 2 locations. Okay. Now let's go to the second one. 2 G's, 2 C's, this one. Now let's start from the first one. Is 55 adjacent to 50? Yes. And 620 is adjacent to 50? We should check the entire list. Okay? We cannot ignore one of them, even if we check it before. This is very important. So the 620 is adjacent to 15? No. Is it adjacent to 615? Yes. So we have 2 locations now. Now we repeat the same thing for those, and luckily they are not adjacent. Okay. Should I repeat it? Okay. All right. So now the third came from the second read, which is 5As. Now we said we have 2 adjacent k-mers at this location, but those are not adjacent. So we need to check one by one for all of them. 55 adjacent here, no, maybe here. No, this is backward. You could apply it if you want, if you assume so, like not considering always the forward path. You could follow the backward, right? And actually, we do it in real life. Why is that? Because we have the DNA strand, and we put it in the machine. The machine starts reading character by character, right? But we don't know whether we are reading from the first character or the last character, right? So we always do the mapping backward, forward, or forward, backward, okay? So if you assume so, it's okay. If you don't assume it, it's correct again. Because based on the definition, it should be in the forward direction. We always have the plus sign, okay? Okay, so we are comparing now 55 with this. No, it's too far, too far, too far. So this one, no, we should ignore it. Now 620 is, oops, sorry. So this is the third k-mer, right? And this is the second. So this should be an increment of this, right? Yeah. So this is correct. Yeah, it's good that we mention it because to know that there's a forward and backward direction. So anyway, this 60 is next to 55, so it's correct. So we should keep this potential mapping, let's call it. And now 620, we should look for 625 here, which is this one. So we have it there. So this is a correct match. Now here, 650. What's next should be 655. Do we have it here? No. Okay. Yeah, anyway, we shouldn't continue, right? Because they were not matched from the second k-mer. So we have only those 2 positions, which is, the first one was here, right? So we have 50 and 615, and from the second k-mer, 55, 620, and from here we have 60 and 6025. So we have 2 mappings for the second read. Now you can repeat this exactly the same steps. Do you want me to continue? How many of you want me to continue? Okay, good. So we have 2. Here we have 0, I guess. Here we have 1 and 1. So in total, we have 5. 5 times we need to perform edit distance. So apparently, this smart way of using adjacency filter, reducing the number of times need to perform edit distance, which is very expensive because quadratic time, from 51 times only to 5 times. So you can see a huge reduction in the execution time of this software. Yes. What do you mean comparing?
Since now we are applying edit distance 15 characters instead of 5.
No, the edit distance here between 15 character, right? So the read length is 15, right? So this location of the k-mers, which is starting from 50 to here, 60 plus 5, which is the end of the k-mer. This is the start index of the k-mer. So you need to add 5. So again, this is 15. So the length of this, the length of this is 15 again, right? Similar to the length of the read. So you have from 50 to 65, this portion in the reference. The reference is 3 billion character, around that, 3.2, okay? So we only go to the location 50 all the way to 65. And then we pick this string, we go to the read, and we compare them together. Now they are equal length. Okay, so now let's use another method. Yes?
I just still don't understand why you perform those 5 edit distance. You know that the distance is 0, right?
Yes, that's true. Okay. That's a good question. But again, we mentioned that the distance between the cameras is considered 0 for simplicity of the calculation, right? But if I consider it to be 1, for example, then you don't know whether this 1 is insertion, deletion, or substitution. unless you try edit distance algorithm. This is in case I allow for a distance between two k-mers to be 1, for example. But here, in this question, I ask you to keep the distance between the k-mers as 0. Okay? But that's true. Maybe we should try it. Let's have this question in the exam. Let's try the distance between the k-mers to be, for example, 5. Let's see. Okay? Yeah, that's a good point. So again, if you are not sure about any point in the exam, you need to assume it. Otherwise, you won't solve the question. Okay? But if the question asks you for something very strict, you cannot assume in this case. Right? Okay. Yeah, some people were like writing half page of assumption, which is invalid. That's not true. Yeah, you cannot just write whatever you have in your mind. It should be valid, should be logical, should be following the given points in the question. Okay? Yeah, we still have the third question, which is some smart people like you proposing another method, which called cheap k-mer selection. So now let's try and see whether that improved the execution time or the number of times we are executing this edit distance function or not. So let's go back to the read. So we have the read set, and the definition of cheap k-mer. Luckily, you got all those definitions, so you don't need to memorize them, right? So we defined already this method, and whatever new algorithm we propose in the exam will be defined. Okay, just you need to follow the definition. So it says you have a threshold, and whenever you have many locations, more than the threshold, you just ignore this k-mer, or you don't perform at the distance. Okay, as easy as this. And what's the threshold here? The threshold is set to be the threshold is set to be 4 here, and so now the question, do we need to apply this cheap k-mer selection on the solution we perform in B or A? Why? Do we mention something about it? Okay, it seems we didn't mention about it. So again, you can assume it here. So you can assume that I'm going to follow the adjacency filtering and applying the threshold together. That's true, it should be correct. Or I'm going to change step 3 here and apply the threshold, where here doesn't mean I have adjacency filtering, okay, which is here, the original question. Okay, so both of them is correct. So now we go here, we pick the first k-mer, here, and we go to the hash table, 5 A's, we got 6 locations, 6 hits. Now, my threshold is 4, so anything exceeding 4, not equal or greater, but exceeding 4, we are going to ignore it. So we ignore those 6. We could say that we will consider only 4 locations without ignoring the seed, meaning that I'm going to consider those 4 locations and ignoring those 2, for example. If you assume so, it's correct. Okay? Now we go to the second k-mer. It's less than 4, so we apply here for each location an edit distance algorithm. So you have 3 times and 0 time from the previous, if you assume so. And then you have 5 G's, which give you 3 locations, so you need to apply here 3 times edit distance. Now this is for the first read. You could do the same thing. Let's take, for example, the last one. So you have 5 A's, 6, the same thing applies here. It's up to you. You want to consider 6 location, or you want to consider no location, or 4 of them only. But you cannot consider 6 because the threshold is 4. So the second k-mer is 2 G's, 2 C's, 1 T. You got 5 locations. Same thing you could do to the 5 A's. Where the threshold is 4, so you can consider the first 4 locations, or you ignore this one. And then the last Kmer here, it's 4 A's, 1 C. 4 A's here, so you got 3 locations. Sorry, on safe side, you can apply edit distance to 3 of them. Yes? Yes. Violating the question. Yes, that's true. That's true. Then our assumption is not valid. Okay? So you cannot, if there's 6 locations, you cannot consider 4 of them and ignore the rest of them. Okay? So if it is exceeding, just ignore it. As simple as this. Okay? So yeah, you can assume whenever it makes sense for you to solve it, but you have to be careful about what the question asks you to solve. Okay? Any question? So we have one to solve the next question. I'm not sure. Yeah, let's see. Right, thank you.
Okay, so this question is relatively easy. I think most of you did this correctly on the exam, except the last part maybe, which is also simple, but looks a bit more difficult. Yeah, just to remind you, so I will just highlight the most important parts of this question because the text here is so long. So it's basically like asking you what will happen to those read requests here, like in terms of latency and like how the system that they are executed on behaves. So basically you need to like look at those requests here, which are all read requests to some like specific physical addresses. And then you have the command types that result based on execution of these requests and the state of the system. So you need to figure out basically what's happening, right? So there's some like reverse engineering that has to be done. So basically, in this, like in those physical addresses, we can figure out exactly to which bank and to which row they go based on the information given in the question. So we have a single channel, so we don't care about channels. We have 2 banks and 64 rows per bank, right? And then here we have important information, which is telling us that the most significant bit of the physical address gives us the bank that will service this request. And then the following 6 bits of the physical address determine the row. So basically, if we like write this in binary format, which is like, is this correct? Yeah. And then 7 is this, right? So we don't have to write all of them because we need only the most significant 7 bits to figure out what is the bank and what is the row, right? So for example, here, by looking at those in like binary form, we can easily tell that the bank is 1. So for this request, it targets bank 1 because the most significant bit is 1, and then the next 6 bits here are 43. So the row is 43. So we have to do it for each single request here. It's not too much work. So this is this, and then this is 8. Oops. This is 1, 1, 0, and then 4, 0, 0, 1, and then 8, right? And so if you do the same here, so for the bank it's very easy, right? So the bank is just, the second request is bank 0, third request is again bank 1, and then bank 0. Okay, and for the row, we look at the next 6 bits. So here it is 20, those bits. And then the next request also, it goes to 50. And then the next goes to row 20. Okay. And basically, if you look at those commands here, so we see that the first command that the memory receives is read, right? So it means that for the requests here, we have the row already open, right? Okay, so and here in this text here is like given necessary information that you don't know the initial state, right? So since the first command here is read, we can tell that bank bank 1 had row 43 open. So I'll just write it like this. So we can figure out this information, right? And then the next command is precharge. So since this comes right after the next cycle, so this could be either precharge for precharge to again bank 1 or bank 0, right? But since it comes right after the next cycle, it's more likely to be a different bank, right? Because I mean so we know that usually there's some like latency between like read and precharge operations, and hopefully it's more than one cycle. So here, yeah, we can assume that this goes to bank 0. So the next precharge is, so we are precharging bank 0. So since we are precharging here bank 0, we know that bank 0 didn't, bank 0 had a row open, right? But we don't know exactly which row was open. So, but we know that it was not 20 at least, but we don't have any other information. So this is relevant to one part of the question, which is part B, but we can like do it like based on this information that we figure out. We can just fill this part, right? So we know that both rows are open because for bank 0 we had to precharge the row, and for bank 1 we service the read request, right? So the initial state is open for both, but bank 0 had 43 open. But for bank 1, bank 1 was 43, and for bank 0, we don't know which one. The only thing we know is it wasn't row 20, right? Okay. Okay, so if we continue here, we can figure out more information. So for example, here at cycle 8, we get a precharge command, right? So we already precharged bank 0, so this is guaranteed to be bank 1, right? And then since this is bank 1, and we waited for exactly 8 cycles here to issue a precharge, we know that the timing parameter here between read to precharge is 8, right? So this here, let me use a different color. So this is 8 here. So yeah, read to precharge latency is 8 cycles. So we have the frequency given here. It's 1 gigahertz, which translates to 1 nanosecond per clock cycle, right? So if we have 8 cycles here, we can fill it in here, right? So it's 8 nanoseconds. So here in part A, if you remember, it asks us to fill in the timing parameters in terms of nanoseconds, yeah. So here, or right unknown. Okay, so we figured that out, and then we have an activate here. So since we first issued a precharge to bank 0, this activate is also bank 0, right? So since we started this precharge later, it cannot complete before this precharge. Okay, so this activate is bank 0, and we are activating for this row over here, right? So we are activating row 20. So this is also telling us what is the distance between like precharge and activate, right? So it is like 12 cycles here. So the precharge to activate latency is 12 nanoseconds. Okay, so let's continue. Then we have a read. So the only active row we have is bank 0. So this is like access to bank 0. So basically, we are completing this request over here, right? So we already completed this one with this read. So now we are completing this request here. So the activate to read latency here as 5 cycles. So we got that too. Yeah, activate to read latency. This is 5 nanoseconds. Okay, and then we have another activate. So here again, we can see that pre-charge to activate latency is 12 cycles, right? And then we have read. Again, this is okay, so this read, okay, so this part is interesting. So we have 2 identical requests here to bank 0, right? So they both target the same row, but different columns of that row. So while this is being activated, so this activate is bank 1. While this is being activated, we can service this last request from bank 0, right? Which also targets row 20. So basically, we have row buffer hit here. So this is telling us the distance between 2 read commands, right? Which is 4 cycles here. So read to read latencies 4 nanoseconds. Okay, and then we basically complete by servicing the last read request, which is here the third request in this order here. Okay, so one thing that we cannot figure out here in this table is the second part, activate to precharge latency. So this is unknown, right? And we cannot tell exactly what is that because we never see here in this like command trace, we never see activate to precharge, right? So we have precharges here, but we don't know exactly at what point activate has been issued to that bank, right? So we cannot tell exactly what is the latency. Maybe we can bound it a little bit, right? So it is, yeah, we can't even bound it, I think. Yeah, so it's unknown. Okay, so is this part clear? Okay, I guess so. And the next part is about TLDRAM, right? So if you remember TLDRAM from the class, basically it is dividing a subarray into 2 parts, into like fast region and slow region. And this table here is giving us how the access latency, how those like timing parameters change when you are accessing the fast or slow region, or near and far segment. The far is the slow region, right? Yeah, and the question is basically giving us the number of cycles that take to execute these requests here if you have a TLDRAM where the near segment, the size of the near segment is defined as n-1, right? So the rows from 0 to n-1 are in the near segment. So we don't know what is n. And the rest are in the far segment. And then the question is telling us that with some value of n, it saves 2 cycles in the overall execution time. So previously, we completed those 4 requests in 25 cycles. Now with TLDRAM, for some like specific value of n, it completes 2 cycles earlier in cycle 23. So we need to figure out basically what is the n here. So there is an so how you should approach this problem is you can easily eliminate some values of n, and then you can like check much smaller number of them. So if you look at here, so we kind of like reverse engineered here the banks and rows, right? So we have only a few ranges here. So we have like rows from 0 to 20, right? That like could cause a difference basically. So all values from 0 to 20 are equal, like in terms of, so they will all result exactly in the same execution time when we use TLDRAM, right? Because we don't have any rows in between. Okay, so the ranges we have to check for n is like one value between 0 and 20, and then one value between 20 and 43, and then 43 to 50, and then more than 50. But here, so we can easily eliminate some ranges, right? So we know that it completes 2 cycles faster. So we can easily tell that so we shouldn't have all of these rows that are accessed here in the far segment. Because if that's the case, we cannot save any latency, right? We will have some overhead. Okay, so we don't have to check the case where n is smaller than 20, right? So we only have to check other regions here. And if you just go in order, I think you will figure out that the range from like 20 to 43 doesn't work. So you get something, I think, bigger than 2 cycles here. And then if you evaluate for n, where n is bigger than 43, so it's like bigger or equal to 43, and then smaller than 50, right? So we have those 2 rows, row 20 and row 43 in the near segment, and row 50 in the far segment. We get exactly 2 cycles of execution time saving here. And then what you need to do is basically, for those ranges, basically redo what will happen to how those requests will be serviced, basically. Because you know everything you need to know to like run the simulation, right? So you know the initial state, you know the request, which banks, which rows that they target, and based on that, you can like simulate a new command trace here. And yeah, basically, once you do that, you will like see that this works fine, and it gives you exactly 2 cycles of latency saving. Okay, I think that's it. We don't have part D. Do you have any questions? No? Okay.
Yeah, in question 3, it's about memory scheduling, and we have to calculate what's the stall time for each application for different scheduling policies. As explained in the question, there are 4 different DRAM commands. We have the activate and pre-charge commands that are essentially opening or closing a row, and then we have read and write commands. In the figure, what we have is a snapshot of a particular point in time where we have a certain number of requests to different rows in 2 channels. So each of these requests go to a different row, meaning R3 meaning to the 3rd row, R5 to the 5th row, and so on. And we have 3 different applications running. So we are going to calculate, we're going to see how the different memory scheduling policies affect the different applications. And we will calculate what's the total latency for the different policies. So let's start with section 3.1, where we are going to deal with application-unaware memory scheduling policies. So essentially, there are 2 memory scheduling policies considered here. The first one is first come, first serve. And the second one, as you know, is going to exploit row buffer locality. It's FRFCFS. So let's first take a look at question A in 3.1. It says, using first come, first serve scheduling policy, what's the stall time of each application? So it is first come, first serve. So this means that the memory requests are going to be processed or are going to be scheduled in the order they arrived to the request queue. Observe that in channel 0, row 3 is open. In channel 1, row 12 is open. So this means that the first request that is going to be consider R3 in channel 0 is going to hit. Similarly, request 12 in channel 1 is also going to hit. Because the policy that we are going to use here is first come, first serve. The next request to be scheduled in channel 0 is request 5, so this one is going to miss. We need to close row 3, and then open row 5. Again, the next request is to row 3, so we will have to close row 5 and open row 3. So this is, again, a miss. For R9, also a miss. R12, also a miss. R3, again a miss. And then, because R3 will be open, we have a hit for row 3, and then miss, 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 and miss. So we can, for application A, in the end, the total stall time will be the maximum in the two channels, channel 0 and channel 1. So in channel 1, for application A, you see that this is the last request from application A. So if we count the number of hits and misses here, we see that there are 2 hits plus 1, 2, 3, 4, 5, 6, 7, plus 7 misses. For application B, again, the maximum of the 2 channels. For application C, it's also the maximum of the 2 channels. So we see that the last request from application B is here, is this request to row 17. So essentially it's the same as application 4, application A, plus 1 more miss. And the last of the request is R21, is from application C. So then it's 2 hits plus 9 misses. So in channel 1, we see that after this hit in row 12, this is a miss, miss, miss. These are all misses. So for the 3 applications, we have 1 hit, which is the first one, the first access, and then a number of misses, depending on when they finish, when they have their last request. This is the last request from application B, the last request from application A, and the last request from application C. They will have 9 misses, 8 misses, or 10 misses. So that's the way we have to proceed in part A. In part B, now we consider first ready, first come, first serve. So again, we will see for the 3 applications, A, B, and C, the maximum in both channels. And we see again that, so we start with this request to row 3, essentially because the row 3 is open. So we are going to choose a request that hits in the row buffer, in the local row buffer. This is a hit. And because the row is open, we want to schedule all requests that are going to hit in this row. So this is also a hit, 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 and hit. So we can already see that for application A to be completely scheduled, we will have to consider these 5 hits plus some number of misses, in particular miss when accessing row 5, miss when accessing row 9. So this is plus 2 misses. So then, if we consider application B, observe that here, once we have finished with request to row 9, the next request is to row 12. This will entail a miss. Next one is to row 11. This is also a miss. And the last one is to row 17. It's also a miss. So we have 3 more misses. 5H plus 5 misses. And for the last of the applications, for application C, we again see a miss for this request to R21. So we have to add 1 more miss. We can proceed similarly in channel 1. So, sorry. So we have a hit to row 12. Because row 12 is open, we keep it open so that we can hit here and here. These are 3 hits. Then there are no more hits from in row 12, so we have to close row 12 and open row 18. This entails a miss, but observe that we also have one outstanding request to row 18, so this is a hit. And finally, to row 19, we again have a miss. So this, for application B, you can see that we have 4 hits plus 2 misses. Next request in the queue is to R3 from application A. So this is a miss. Row 1, again a miss, miss. And the final one is R2. So we are adding 4 more misses for application A to finish. We have to wait for 4 hits plus 6 misses. And finally, for application C, we have a miss in row 27. So finally, we have to wait for application C 4 hits plus 7 misses. So this is if we apply the first ready, first come, first served policy. You see that the problem with this policy is that it doesn't take into account the individual characteristics of the applications. So for example, even though it's efficient from the point of view of row buffer locality, actually that's related to the answer to question C, that it's efficient from that point of view, it might unfairly delay some of the applications. In this case, you see that even though application C has only 1 request in the queue, it has to wait for all the applications to finish. So that's why in the next part, in 3.2, we are going to consider application-aware memory scheduling. The last question in 3.1 says, describe briefly the scheduling policy that would maximize the request throughput at any given bank. This is first ready, first comes, first serve. As you can see, it's the memory scheduling policy that we have been considering in this first part. So as I was saying, in the second part, in 3.2, we want some scheduling policy that is aware of the behavior of each application. So in particular, part A proposes a policy called scheduling policy X, where application C is going to be prioritized because of the fact that it's the one with the least number of memory request, so we don't want to unfairly delay it. So that's why we're going to prioritize application C. So, because application C is priority, the first request to be solved in each of the channels is R21 and R27, respectively. And so we will need to close row 3 and close row 12 in channel 1. This entails a miss in row in request 20 for request 21 and a miss for request 27. So for application C, the stall time is going to be the maximum of M and M, because we have 2 misses. Then, let's see what we have to do with application A and with application B. The question says that for 2 applications with the same priority, and A and B have the same priority in this part of the question, we are going again to apply first ready, first come, first serve. So after in channel 0, after serving request 21, we will serve request 3, for application A. This is a miss, and this will hit here, 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 and here. And then, once the requests to row 3 have been completed, we continue with the next request, which is R5. The next request to arrive to the queue is to R5, so this is a miss. Then R9, and this is a miss. So for application A, we have 4 hits plus 4 misses to bank to channel 0. For application B, after finishing with all the requests from application A, we still have to service this R12, provoking a miss, then R11, a new miss, and R17, a new miss. So that's why for application B in channel 1, we have 4 hits plus 7 misses. And now let's take a look at channel 1. For channel 1, after serving this miss, this access to row 27, we go to row 12. And once row 12 is open, we can hit with this request and hit with this request from application B. Then we go to the next request in queue, a miss for R18, and then we can hit here. And finally, a miss for R19. So in order to serve all the requests from application B, we have to wait 3 hits plus 4 misses. And we will finish with request from application A. This is a miss. All these are misses. So for application A, we have to wait for 3 hits plus 8 misses. Is that clear? Any questions? Okay. So then the last part of question A says, can you design a better, an even better scheduling policy? Well, this is like an open-ended question, so you can answer many different things. You can come up with some strategy that prioritizes, I don't know, for example, because in the beginning of this question A for policy X, we have considered that we want to service application C first because it only has 1 request in each queue. So we could, for example, consider a similar policy for the other two and say, okay, we are going to count the number of requests coming from each application, and in order to not unfairly delay them, we are going to prioritize them in the opposite order, that the number of requests that they have. So for example, in channel 1, we would prioritize application B with respect to application A. That's a possible policy, and that's a possible answer for this for the end of question A. Regarding question B, we actually going to assume something like that. I mean, what we propose is assign priorities to the other two applications such that you minimize the average stall time across the applications. So what we can propose here is that C has more priority than B and B more priority than A. So this is a new scheduling policy, and we are going to consider this new scheduling policy for part C. This is policy Y. It says, using our new scheduling policy, what's the stall time of each application? So again, the highest priority is for C. So these two misses are first serve for application C. Is the maximum of M and M. And then the priority in both channels is going to be application B. So we first we will serve this row 12, provoking a miss, row 11, and row 17. So for application B in channel 0, we have to wait 4 misses. In channel 1, we have a miss here, then we can hit these 2 rows, then again a miss, we can hit here, row 18, and then a miss. So in channel 1, we have to wait for 3 hits and 4 misses. And then let's see what happens for application A. In channel 0, after these 4 misses, we have a miss in row 3. This is a hit, hit, and hit, and also here one hit in row 3, and then a miss, and then a miss to serve row 9. So finally, we have to wait for 4 hits and 7 misses in channel 0. In channel 1, we will have misses for all the remaining requests from application A. So finally, it's 3 hits plus 8 misses. And that's actually all. I mean, the last part, D, says order the 4 scheduling policies in the order of lowest to highest average stall time. As you will have calculated the stall time for every application and every policy, you can calculate the average, and you'll see that this is the order. So that's all regarding this problem 3. Any questions? Okay.
Right, so for this question about emerging memory technologies, it's a bit straightforward and easy question. So you have a computer scientist at ETH developed a new memory technology. They call it ETH RAM, which is non-volatile. And the access latency of this RAM is close to that of DRAM, while to provide higher density compared to the latest DRAM technologies. So this RAM has shortcoming, which is limited endurance. So, which means the memory stops functioning after some series of write requests to that memory. And basically, it's 10 to the power 6 write request, then the cell will wear out, which means the RAM will be useless in this case. So we have a student, female student, and build a computer system using 1 gigabyte of this RAM, and this is very important, basically. So she exploits a perfect wear leveling mechanism, which means there is a perfect distributor that distributes those write requests to all cells. So you have fair write requests among the or all over the RAM. So this student now worried about the lifetime of the computer system she built, and she execute a test program. She want to know basically after how long the RAM will be useless. And she figured out that after a year, exactly a year, this ETH RAM will be useless. So you have the following assumptions. So the processor is in order, and there is no memory level parallelism, which means that you have all those write requests serially sent from the processor to the RAM, and you cannot write more than one row per time. So everything in serial fashion. And it takes 5 nanoseconds to send a memory request from the processor to the controller, and then from the controller to the RAM, it took 28 nanoseconds. So basically, this RAM is word addressable. Thus, each write request write 4 bytes for each write request. So basically, you could assume that this is the RAM, and you have rows. The size of this RAM is 1 gigabyte, and you need to know basically how many rows you have there. And yeah, sorry, the question is, ask you to find the write latency of that RAM. So you already know that this RAM will be wear out after 1 year, and you have all the latency requests from the processor to the controller, from the controller to the RAM, and you need to figure out basically the write latency. So how many rows we have in this RAM? If you know that the one row is 4 bytes, then obviously 1 gigabyte over 4 bytes, you will get how many rows there. And each row has many cells, and each cell will wear out after 10 to the power 6 write access to that cell. So basically, the time to wear out the entire RAM is equivalent to how many rows and how many times you are able to access that row at most, plus the delay to send the write request to the RAM and the write latency. So basically, this is equivalent to 2 to the power 30. You divide over 2 to the power 2 to know how many rows, and each row you could access it at most by 10 to the power 6, and then multiply by the total time needs to access that RAM and write some data, which is basically 5 plus 28 plus the write latency. So let's call it write, for example. And this is equivalent to 1 year. So now you need to make sure that all the units are consistent in this function. So here you have byte, byte, and here you have nanosecond, nanosecond. So this should be nanosecond, as well as the 1 year you need to convert to nanosecond. So then you'll have your function, which is 365 multiplied by 24 hours per day, and then convert it into seconds, multiplied by 10 to the power 9. Okay. So basically, you could divide this over, so we have 28. So you could divide over 2 to the power 28, multiply by 10 to the power 6. This will give you 5 plus 28 plus the t right. So this is 32, 33. So you could move it to the other side, and then you will get the write latency, which is equivalent to 84.5 nanosecond. So this question is straightforward, easy to solve, I guess. So do you have any questions? All right, cool. So let's proceed to the second part of this question. So now you need to follow the exact same procedures, but you need to change a bit in the design to improve the lifetime of this DRAM, or sorry, the ETH RAM. So basically they assume that the previous design has 2 bits in each cell, and now they will reduce it to 1 bit. And this affects the lifetime of each cell, and they improve it by 10x. However, this as well decreased the write latency by 70%. So now we need to calculate the same steps to get the new lifetime of this ETH RAM. So let's start from the 10x. So basically, in the first part, the cell was will wear out after 10 to the power 6. So now 10x higher. So basically, it will be 10 to the power 7, right? So 10 multiplied by 10 to the power 6. And the write latency decreases by 70%. So the write latency in the first part, we calculated as 84.5. And now we need to have 30% of that time delay for the new ETH RAM. So the new HW2, let's call it, it's 30% of the 84.5. So now you have everything ready, except one thing. We reduced the number of bits to be stored in each cell from 2 to 1. This directly affects the storage or the capacity of this ETH RAM from 1 gigabyte into half, right? Because we reduce the number of bits stored there to half. So this gives us, so now we want to calculate the total time to wear out. So we have 2 to the power 30 minus 1, right? Because we reduced the size to half. And now we have how many rows there? So each row can afford 4 bytes, same thing, 2 to the power 2. Now multiplied by the new lifetime for each cell, which is 2 to the power 7, multiplied by the total time needs to send the request to the controller, from the controller to the RAM, and then the write latency. So however we change the write latency, we improve it by 70%, and we have the new one calculated as 25.35. So we have the same time needed to send the request to the controller and back to the RAM, which is 5 plus 28. Sorry, this is plus. So this will give you directly the answer, which will be 2.5, almost 2.5 years. Any question for that? Yeah, just straightforward, right? All right, thank you.
So this question here is about asymmetric multicore. So I'm going to read the question first. A microprocessor manufacturer asks you to design a symmetric multicore processor for modern workloads. We should optimize it assuming that the workload has 80% of its work in a parallel portion. This is going to be important. Your design contains one large core and several small cores which share the same design. Assume that the total area that you have to place those cores is 32 units of area. So then you have the configurations of the large and small cores. For the large cores, it is n times faster than a single small core, and it takes an area of n cubed units of area, a dynamic power of 6 times n, and a static power of n watts. For the small cores, you can fit as many small cores in the die after placing the large cores. The area is 1 unit of area per small core, the dynamic power is 1, and the static power is 0.5. So they say in the question that the parallel portion executes only on the small cores, while the serial portion executes only on the larger core. So based on those informations, you're going to answer the following questions. So first, they ask what is the configuration, number of small cores and sizes of the large cores is going to result in the best performance. So all of the information that you have here is important. So first, the fact that your application can take 80% is 80% parallel, and 20% is going to be serial. So you know that the speed up is going to be given by 1 over this is the serial part plus the parallel part, and this is equal to 80% of applications parallel, then 0.2% of 0.2 of your application is going to be serial, and out of the large core is n times faster than the small cores, right? So this is going to be n times the rest of the execution, 0.8 is parallel. And how many parallel cores can you fit? You're going to be able to fit 32 cores minus 32 minus the area that you have available, right? So you already placed one larger core, so this area is minus n cube. Any question about this? How I formulate this equation? Quite simple. So we are going to assume that the time to execute the application is going to be the time of the serial part plus the time of the parallel part, and this is equal to the time of the serial part is 0.2 over n plus the time of the parallel part 0.8 over 32 minus n cubed. And then you need to find out which values of n give you the best time, the smaller time. For this, what we can do in the solutions, we test different values of n. So here, for example, you have n equals to 1, and then you're going to have the time for the serial part, the time for the parallel part, and the total time. So if you have n equals to 1 here, you're going to have the serial part is going to take 0.1 divided by 1, 0.2 divided by 1, 0.2, and the parallel part is 0.8 divided by 32, and I have here the number is around 0.03, and the total time is 0.2323 exactly. If n is equal to 2, this is going to be 0.2 divided by 2, that is 0.1, and here is going to be also something close to 0.03, and the total time is 0.13. If n is equal to 3, this time for the serial part is 5, the time for the parallel part is 0.16, oh sorry, this is not 5, it's 0.07, and the total time is 0.23. So you can continue doing this table until you reach the total area that you can have in the chip, but we figure out that actually n is equals to 2 is going to give you the best timing. So if you have n equals to 2, it means that you can place 32 minus n cube, 32 minus 2 to the third, this is 24 small cores, and the area for the larger core, the area is given by the area is n cube, so is 8. Any question about this? So in the solution, we solve it by calculating based on placing values for the table for this equation here, but it's not necessary. You can derivate and find the maximum minimum values here. Also, if you want to guarantee that you find out the best solution. So this is the first question, the first part. Then they ask you to calculate what is going to be the energy for this design, considering that the best configuration that you find in part A. So n is equals to 2. So energy is going to be given by the energy of the small cores plus the energy of the larger core. And the small core, the energy is equals to power versus time. So it's going to be given by the power, the dynamic power for the small core plus the dynamic power for the small core, the static power for the small core times the small core executes only the parallel port, right? The time that it takes to execute the parallel port. However, while the parallel port is executing, while the serial port is executing, this core is still in the die, right? So you need to consider the static energy also that this core is going to take while it's not doing any computation. So plus the power, the static power of the small core while the serial portion is being executed. And for also the number of small cores that you have here, right? You have 32 minus n cube cores, right? We have 24 small cores. For the larger core, we have exactly the same equation. So you have power versus time, and it's going to be the power for the larger core for dynamic power plus the power for the large core, the static power, times the time to run the serial part. And similar to what I did here, we also have to consider the static power while this core is not doing computation, but the parallel part is being executed. So power for the large core, the static power, times the time for the parallel part. That is the time that this core is not doing anything. And if you look at the solution, I'm not going to put some numbers here, is 24, I guess. 26 times for the serial part times 38 times for the parallel part, and this gives you 3.74 joules. The times here are just the times for the serial parallel part that I calculate before.
For these parts, when you're calculating like the time for, when you're calculating like the time for serial and time for parallel, these don't have units, right? Because you're calculating based off like a percentage, and you're applying like the relative like computing power of the dies, right?
So what we know is that it's a ratio in the end. You're right. There is no unit here, because the only thing that we say is that the larger core is n times faster than the other folder cores, and everything is based on this number. So is this the question?
Yeah. So I guess like when we're calculating the other side, the energy consumption on the back, like I can see like that given these numbers that we calculated in the first part, you can compare all the numbers, all the energy consumptions to each other. But is it still possible to like create to have this in joules, because we don't have this in seconds, right?
We can assume, if you assume that the time that the one slow core is going to take to calculate some computation is 1 second, is what I'm doing right here.
Yeah.
Then you can calculate the joule like that. So it's kind of implicit, but you can also do the same in the exam. Any other question? Okay. So for part C, it says that for the configuration obtained in part A, you are considering to use the larger core to collaborate with the small core on the execution of the parallel portion. So now, before the serial portion was being executed only on the larger core, and the parallel portion only on the parallel part. And now the larger core is going to help executing the parallel code also. And the first item that asks you is what is the overall performance improvement compared to the performance obtained in part A if the larger core collaborates with the parallel portion. So the equation that you have is similar than before. So 1 over the time for the serial part does not change at all. So is it still the same? 0.2 over n plus 0.8 over 32 minus n cubed. This is the number of that is going to take, the time that is going to take for the small cores. But now you have some help from the larger core to help you in the parallel portion. And he asks you what is the performance improvement. So for the parallel portion, so before you have that the parallel portion was taking 32 minus n cubed, and now you have that is going to take 32 minus n cubed plus n. Remember that n is equals to 2, because you need to consider the same value that you found in part A of the question. So this time here is 0.8 over 24, and this one here is 0.8 over 26. So the improvement that you're going to have is 1 over the other, and is t over 2, that is going to be 26 over 24, and this is going to be 0.8%ish, around this value. Any question here? Okay. So now it asks also what is going to be the energy now that the larger core collaborates. What the energy change when the larger core collaborates in the parallel execution. So recall that the energy is the energy of the large core plus the energy of the small core. So the equation that you had before, I'm going to reuse the equation because it's quite similar. For the small core, this equation does not change. For the larger core, now here we are not, when the parallel portion is executing, this core is not sitting idle anymore. So the time that is the power that is going to be consumed is not only the static power, is also the dynamic power for this core. times the time for the parallel portion. So this is the only changes in the equation that you have. And this is going to lead you to energy. I'm going to check in the solution is 26 times the serial part, same as before, and now it's 50 times the parallel portion. Pay attention here how much the energy expended on the parallel portion increases now, because recall that the dynamic power for the serial part, for the larger core, is 6 times larger than the 6n, while for the other core is just 1 unit of it was 6n over n. I forgot actually. Oh yes, it's only 1 watt and the other one is 6n watts. So the larger core takes significantly more amount of dynamic power to execute than the small core. And this is going to give you 3.74 joules. While the other one, no, this is wrong. This is the other one. This is 4 point something. 4.6. While the other one was 3.74. And then the next question is, does it make sense to ask the larger core to help in the parallel portion? Because you have a 8% improvement in performance, but at your energy increases from 3.74 to 4.6. So an idea if it makes sense? What you guys think? So does not make sense, right? Because your energy is going to increase a lot when if you execute in the out of order core. If you want to make sure if it makes sense or not, there is one metric that is called EDP, energy delay product, that measures actually the trade-off between energy and time, or power and time consumption. So this equation is pretty much energy times time. So if you calculate the EDP when the out of order core, no, the larger core is not helping, we are going to have that the energy we spent was 3.74 joules and the time was 0.13. And this is going to give you, let me check my number, 0.48. While the other core is helping, the large core is helping, this energy goes up for 4.6 joules, and the time reduces by 8%, is around 0.12ish. And this is going to give you 0.55 something. So this metric, lower is better, so it does not make sense.
Do we have to compute that metric?
You don't have to compute the metric. If you have the solution, you can just justify saying that does not make sense because of this argument of the energy increases and the performance does not improve that much. But if you know the metric by head and want to make sure that is the case, you can use the metric.
Also, are we not allowed to use calculators for this exam? Because I feel like this question is very computational.
You are not allowed to use calculators in the lab for the exam. Most of the time, if you just place the equation there, we are going to grade based on the if you assemble the equation properly. If you want to do the computation, you can approximate, is what we say here in the exam. Yeah, so if you need to do the computation, you can approximate. For example, for the first part, you need to do the computation, right, to figure out the timing. So you can just approximate. You can approximate using some values.
Should you approximate like 2 decimal points, or like what do you think?
2 decimal points is already fine. Yes. Okay. Part D. Now assume that we are going to optimize the serial portion of the code, and the serial portion is going to become smaller. This gives you the possibility to reduce the size of the large core and still improve performance. For the large core with an area of n-1 to the power of 3, where n is the value obtained in part A, so it's still 2, what should be the fraction of the serial portion that will lead you to a better performance than part A? So, solution is here. So we have that the serial portion, we don't know anymore how much is the serial portion, right? But we know from the equation that is 1 minus the parallel portion. And the time that is going to take for the executing the serial portion, we are going to assume that is proportional to the area that you have, because now you have a smaller core, so it's going to take this core is not going to be as faster, right, as before. So it's going to assume that this is proportional to the area, so it's going to take n minus 1 units of time to execute the serial portion. The parallel portion still takes p units of time, and we still have the same amount of area, so we can place 32 minus n minus 1 to the power of 3 number of small cores. So we want this, we are going to assume as before, the time is going to be given by 1 minus p n minus 1 plus p 32 minus n minus 1 to the power of 3. And you want this time here to be smaller than the previous time, right? That was 0.13 from the calculate in part A. Assuming that n is equals to 2, you have that 1 minus p, this is going to be 1 plus p 32 minus, this is 1 also, so this is actually 31. Should be smaller than 0.13. And you do the calculation, you're going to be find out that p should be larger than 0.9. So the parallel portion should be larger than 9% of the execution time now, if you still want to have performance improvements. But he is asking about the serial portion. So the serial portion can be at most 10%, right? Is 1 minus 90. 0.9. Any question?
For the 1 minus p portion, how come we don't divide it by n equals 2, making it that 90% of it is computed by n times faster than the small core? Because if you divided p divided by 31, so I don't get why we don't divide 1 minus p by the speed it computes at.
So I don't understand your question, but let me try to explain again. This portion here is the serial part, right? So I'm dividing this one here by 31 because of the amount of small cores that you can place, right? The amount since we know that the amount of small core that you can place is 32 minus the area of the larger core, because we place it first. So it's going to be 32 minus n minus 1 to the third. And here is just the serial portion.
But I don't know why we're dividing by area instead of how fast it computes.
It is by how fast it computes. We know that a large core is n times faster than the small cores. So we are using this information, and this information is related to the area. We are assuming that the execution is perfect, and the small core is always going to be n times slower than the larger core. So one small core always n times is lower than the larger core itself. Does it make any sense? I think it's related to the same question that he asked before, but maybe we can talk after I finish here. Anyone has the same question? Okay. So finally, your design is successful for desktop processors and your company wants to produce similar design for mobile devices. The power budget becomes the constraint, and you have maximum power that you can expand of 20 watts. And they are asking you how much you need to reduce the dynamic power consumption of the larger core, if at all, for the best configuration of obtaining part A. Assume the parallel function is the same as before, 80% of the workload, and the dynamic power, they give you a hint, the dynamic power of the larger core is D in watts, where D is a constant. So before it was 6 n's, now it's D. You want to figure out D. So we know that energy is equals to power times time. So this means that power is equals to energy divided by time, right? And you want your energy to be at most 20 watts. And the same as before, the energy here is going to be the energy of the large core plus the energy of the small core divided by the time, the total time. So this is going to be equal to the power times, this is the energy is power times time. So this is the dynamic power for the larger core, that is D, right? Dn, plus the time for the serial portion, plus the, I should have done this, plus the static power, this is dynamic power. The static power is still the same as before, n, so n times this serial, this is the then static, dynamic, plus the time that it takes for the, oh, this is going to be a count later, plus the energy for the small core that you have before. I'm missing something? I feel like I'm missing something. Oh yes, I'm missing it. Plus the time for the static power. So n, this is the static power for the large core, times the time that is sitting idle, right? Parallel portion, plus the energy for, I already counted, energy for the small, so the equation is done, divided by the total time, 0.13. So this is G plus 1 n times T serial plus n times T parallel plus the energy of the small core divided by 0.13, should be smaller than 20. And then you're going to figure out, when you do the equation, you place n is equal to 2, you're going to find out that D is equals to, should be smaller than 0.3. And is asking how, assume how much you need to reduce the power, right? So we know that now the dynamic power is 0.3 n, and before the dynamic power was 6 n, right? Was here somewhere. Is 6 n. So this is going to, so we have that. You're going to have that this is a, you have to reduce the dynamic power if you divide one by the other by 20 times if you want to maintain the same performance as before. So any question about this? Okay, so the next one.
This in particular is from the final exam from the fall 2017. Programmer writes the following 2 C code segments. She wants to run them concurrently on a multi-core processor called LSC using 2 different threads, each of which will run on a different core. The processor implements sequential consistency as we discussed in the lecture, and this is the code that the 2 threads execute. It's very simple. As you can see, each of them composed by 4 instructions. X, Y, and flag have been allocated in main memory, while A and B are contained in processor registers. A read or write to any of these variables generates a single memory request. The initial values of all memory locations and variables are 0. Assume each line of the C code segment of a thread is a single instruction. That's important to keep in mind. And then part A asks what's the final value of Y0 in the SC processor after both threads finish execution. Explain your answer. So the first thing to recall here is that the sequential consistency ensures that the order in which memory accesses from a particular thread, from a particular core, are going to take place is the same order as we have in the program, and that's very important in this processor to confirm that this update here by instruction T11 is going to happen after this one here from instruction 10. Another thing to observe here is that we are using this flag to synchronize in some way thread 0 and thread 1. Observe that this instruction T02 is a while loop where the thread 0 is going to check what's the value of the flag, and while the value of the flag is 0, it will keep looping there. It's kind of busy waiting, and only after the flag is set by thread 1, thread 0 will leave this while loop and continue to the execution of T03. Right? So if we take these things into account, we will see that the final value of Y0 is equal to. And why is that? Because in the very beginning, T1 initializes that position equal to 1 and then sets the flag. And because this is a sequential consistency processor, it's we can be sure that this flag update will happen after this Y0 update. And because of that, the next thing to happen is that after T1 sets the flag, thread 0 can leave this while loop and then execute instruction T03, and the final result will be equal to. Make sense? Okay, now it says, what's the final value of B in the SC processor after both threads finish the execution? Let's see, what can I do? So I want you to see the code while we do the reasoning here. So for B, what we see is that there are two possible orderings in the execution here. The first ordering, let's call it O1, happens if T10 is executed before T01, and the second possible ordering happens if it is the other way around, right? T01 happens before T10. Why is this possible? Because across threads there is no way of enforcing that this T10 happens before this 01 or the other way around. So we don't know how these two memory requests are going to be served, and based on that, any of these two orderings could happen, right? And if you check, in this case, you check it by yourself. In this case, the final value of V is going to be 1, and in this case, the final value of V is going to be 0, right? So if this one is executed before this one, Y0 will be 0 in the execution of this instruction, right? And that's why B is finally 0. But if this was updated before, then what we will have in B is 1, which is what happens if the ordering, the sequentially consistent ordering that finally happens is 01. So the question is if T13 could happen before T01. I think so. I think you're right, but you know, this doesn't change the final result because X0 is 0. You see? It is true that the solution didn't consider this ordering, but yeah, the result would be the same. Okay, that's a good question. Okay, now what do we have next? It's part C. And part C says, with the aim of achieving higher performance, the programmer tests her code on a new multi-core processor called RC that implements weak consistency. As discussed in the lecture, the weak consistency model has no need to guarantee a strict order of memory operations. For this question, consider a very weak model where there is no guarantee on the ordering of instructions as seen by different cores. What's the final value of Y0 in the RC processor after both reads finish execution? Explain your answer. So, in this case, let's go again to take a look at the code. Here is the code. So in this case, we have three possible orderings from the perspective of T0. So the first one, let's call it O1, consists of T10 executing before T11 before T03. Ordering 2 is T11 before T10 before T03, and ordering 3 is T11 before T03 and before T10. Observe that here there is no, no guarantee of any ordering within the same thread, right? That's why T01 can happen before T10, T10 can happen before T11, or the other way around, which is
what we see in O1 and O2, and similarly this T03 could even happen before T10. Why is that? Because in the end, the only thing that we can be sure is that T03 will happen after T11 because of the flag, right? Because thread 0 will not issue this T03 instruction until it leaves the while loop, but there is no ordering guarantee for this T10. So that's why we can have 3 different orderings. So in this case, the final value, it's going to be 2. In this case, final value is 2. And in this case, final value is 1. Okay? Okay. And finally, part D. After several months spent debugging her code, the programmer learns that the new processor includes a memory fence instruction in its ISA. So it's important that you take a look at the ISA before programming a computer. The semantics of the memory fence is as follows for a given thread that executes it. First, wait, stall the processor until all preceding memory operations from the thread complete in the memory system and become visible to other cores. Second, ensure no memory operation from any later instruction in the thread gets executed before the memory fence is retired. So, in the weak consistency processor, we definitely need to use fences whenever we want to enforce the ordering. There is no other way of having these guarantees. So then part D asks, what minimal changes should the programmer make to the program above to ensure that the final value Y0 on RC is the same as that in part A on SC? Explain your answer. So we obviously need to use this memory fence instruction that we have just discovered and put it in the right place. So what I'm going to do here is simply rewrite the code to modify or include whatever additions are needed there, right? This is T12, this is T13, and here we have A equal X0, B equal A plus Y0. Here we have the while loop with the flag, and here Y0 plus equal 1. And then Y0 is initialized, then we put here the flag, set the flag equal to 1, x1 multiplies by 2, and A0. That's it, right? So if we look at thread 1, where should we place the memory fence or the multiple memory fences? I don't know that. So in the end, if we go back to the where is this? If we go back to the solution of the previous part C, what we saw is that the problem that we have inside the same thread, inside thread 1, is that there is no ordering enforced between these two instructions. So any of those could happen before the other one, right? So if we want to enforce that order in there, the place to put the memory fence is here. right? So this would be now like instruction 1 in thread 1. And also, in order to make sure that this instruction TO3 also doesn't happen before, I mean, in purity, if you look at this code and based on what are the restrictions and assumptions given in the question itself, this should work as is. But in reality, there are multiple accesses here, right, in this while loop, because this is a while loop. Every iteration, the thread 2 is going to go to memory and check if the flag has been set or not, right? So in this situation, if we really want to make sure that everything is going to be executed in the correct order, we need to also place a memory fence here. Okay? So that could be, that is, let's say, the perfectly complete solution. But yeah, this was in an exam. We found that this could happen. I mean, we understood that some people, some students didn't put the memory fence here, and that's why, I mean, that's why I'm clarifying this simply, right? But I mean, in reality, the right way to do it is as you can see right now on the screen. Okay. Any other questions? Okay. Thank you so much.